Imagine building a living organism from individual cells. Once this organism is built, it can move, be programmed, and do several assigned tasks, all without being controlled. After it runs out of food, it dies and is fully biodegradable. Now, imagine if this organism was designed by a computer algorithm. Well, all of this has just happened. This is a fascinating topic, and we'll find out all about it in this episode. This breakthrough follows the recent trend of biological engineering. We've seen biological robots successfully defeat cancers of the blood. Using the body's own immune system to fight cancer is called immunotherapy, and CAR-T is the most promising form of this approach. The reason people are so excited about this is because it produced incredible results in patients where all other treatments failed to work, and stem cells that were injected directly into the brain to restore movement and make the wheelchair-bound walk again. These stem cells then triggered the damaged areas of the brain to repair themselves. Within days, patients could move limbs again and begin to speak properly when they couldn't previously. Those people who saw those episodes were completely blown away, but this latest breakthrough is different. This time, the breakthrough by a team of scientists at the University of Vermont was to create something completely new. It is the world's first living machine designed from the ground up. Joshua Bongard, a computer scientist and robotics expert who co-led the study, sums it all up. What they've created is, quote, neither a traditional robot nor a known species of animal. It's a new class of artifact, a living, programmable organism. So what's going on here? The researchers repurposed living cells scraped from frog embryos and assembled them into entirely new life forms. The original stem cells came from an African clawed frog known by the Latin name Xenobots laevus, but these living robots don't resemble any living creature. After being harvested, the stem cells were then separated into single cells and left to incubate. The cells were cut and joined together under a microscope. The resulting assembly of living cells has been dubbed a Xenobot, and they're tiny, at just 0.04 inches or 1 millimeter wide. These robots can move independently and collectively and survive for weeks at a time. They could potentially be used to transport medicines inside a patient's body, as well as other uses. And don't worry, we'll get to all of this later on in the episode. But the thing about this that amazed me the most was how it was all designed. The new creatures were designed by a supercomputer at the University of Vermont, and then assembled and tested by biologists at Tufts University. Here's how it worked. The Deep Green supercomputer cluster at the University of Vermont ran for months at a time. This computer was custom designed, allowing for cutting-edge AI research.
4 miles east of UVM Central Campus, now home to the university's new supercomputer, dubbed Deep Green, intended for research into machine learning and artificial intelligence. The machine, said to be among the 100 most powerful in the nation,
it's about 800 to 1,000 normal laptops.
One of Deep Green's graphic processing units, removed for demonstration, was impressive enough.
We have 10 of these across the entire cluster. It's almost 500,000 processing cores.
Deep Green exceeds petaflop speed, 1,000 million calculations per second. With its wide-ranging applications,
it is a very big deal. This will allow us to be fairly competitive with much larger universities and allow us to do research that we could not have been able to do.
It used an evolutionary algorithm to create thousands of candidate designs for the new life forms. The scientists determined a desired task. In this case, the task was movement. So, the algorithm would create designs intended to produce the outcome of movement. Within its software, the computer would assemble a few hundred simulated heart and skin cells into different body forms. The behavior of these cells was governed by constraints and parameters. For example, the maximum muscle power of a frog heart cell. With these parameters as its guide, the algorithm iterated the life form designs. The more successful simulated organisms were allowed to reproduce inside the algorithm, while the failed designs were thrown away. After 100 independent runs of the algorithm, the most promising designs were selected for testing, and then, later, brought to life. Lead study author Sam Kriegman speaks, quote, Eventually, it was able to give us designs that were actually transferable to real cells. That was a breakthrough. There's no external control from a remote control or bioelectricity. This is an autonomous agent. It's almost like a wind-up toy. As these biological devices were assembled into body forms never before seen in nature, the cells began to work together. The heart cells, as the muscles contracted, worked to provide an ordered forward motion as simulated and predicted by the computer's design. The contractions of the heart muscles were the mechanisms for motion. The skin cells, on the other hand, behaved as a scaffolding to hold everything together. The organisms managed to survive in their watery environment for weeks. They were powered by stored energy in the form of proteins. The Xenobots moved objects around in the real world too. When their environment was scattered with particles, the Xenobots spontaneously worked together, moving in a circular motion to push the particles into one spot. The robots also had the benefit of healing themselves after being cut. Quote, "We sliced the robot almost in half, and it stitches itself back up and keeps going, and this is something that you can't do with typical machines." End quote. Many people worry about the implications of a rapid technological advancement in ever more complex biological manipulations. Michael Levin of the study speaks, quote, "When we start to mess around with complex systems that we don't understand, we're going to get unintended consequences." It's strange to think that if left alone to their natural development, the stem cells taken from the embryonic frogs would have turned into skin and heart tissue within living, breathing animals. Instead, in configurations designed by a computer algorithm, they were constructed by humans, and those cells were assembled into something completely new, a living, programmable robot. Although the current states of Xenobots is relatively harmless, there is the potential for future work to incorporate a nervous system and countless other applications. This is an immense responsibility for humans to have, and one of the biggest questions to if this should be done or not is, do the benefits outweigh the risks? At this stage, it's impossible to know. Biological unintended consequences are no joke.